So we had capacitors in series where they were connected into basically one path. Now we'll look at capacitors in parallel. And in this case, the two leads of each capacitor are connected to each other, and then each set is connected to the potential source. And we're interested in the capacitance CT across this source VT. So let's think about how this is going to work. We have some charge, we'll call it QT, leaves the positive side of the potential source, the battery, and it gets to this node, this connection point, and it sees three possible paths that it can go to. So you can have a charge Q1 on capacitor C1, or I'm sorry, that's C3. Do C1 over here. So this, you can have Q1 here, amount of charge. C2 can have Q2 amount of charge, and C3 can have Q3 amount of charge. So each of these charges have to be the sum of the total charge. So we have QT is equal to Q1 plus Q2 plus Q3. And now let's look at the potentials. Well, the potential VT is across all three capacitors. So if one of the capacitors had a potential greater than VT, then the charges would move until everything was in equilibrium. And the only way that things can be in equilibrium is if VT is equal to V1 is equal to V2 and is equal to V3. The same potential has to be across each of the capacitors. So let's write down our formulas that we had, the relationships. We had Q1 is equal to C1 V1. Q2 is equal to C2 V2. Q3 is equal to C3 V3. And QT is equal to CT times VT. And I have this sum relationship, so I can substitute these formulas into there. So I get CT VT is equal to C1 V1 plus C2 V2 plus C3 V3. But all of the potentials are equal, so I can factor those out, and I get CT is equal to C1 plus C2 plus C3. And this is the capacitance in parallel. So the total capacitance is the sum of all individual capacitances. My pen quit working. But that's how you get the capacitance of parallel capacitors. Now the next time we're going to work a problem where we're going to mix series and parallel together.